So welcome to video 5 in our course G04 mutation detection, where we're talking about future developments or some brief overview of opportunities in this area. So if we go back to the early history of mutation detection approaches in genomic data, this classic paper by De Fristo et al. In 2011 in Nature Genetics kind of give us a sense of the approaches that are still used today in terms of basic bioprocessing from FASTQ to SAM-BAM, BCF, through to the linkage of different variant types to estimate, go from candidate SNP sites to valid sets for a sample. And we should be aware as well that there's often abundant external data that might be useful for us. So not necessarily pedigrees, but often there'll be other things like databases of SNPs that are known that can improve our estimate of the true SNP set. So this is never categorical. It's never as clear cut as being valid and invalid is often something that improves with time. And what we think about that is that we have sets of VCFs together to assess as a single set. And you kind of see this diagram here. We can imagine that we have multiple samples where we can, if we write our code in the right way, we can do samples in batches. And one opportunity in this area is the creation of a reference graph to represent the different variants that are present in a sample. So we can imagine that each of these samples, 1, 2, 3, 4, up to n, each have its own genetic patterns, its own mutations, and we can represent that as a graph. So we can imagine that we might have a region here that's conserved in blue here. I might have particular samples that have a region A, mutation at allele A or B here, at this pink and green region, and also another one at this yellow and red region, C and D that differ. And therefore, we might have different samples represented as a single graph in a single reference, which is kind of a graphical genome alignment to which we can map our reads. So that might mean that our reads map to, say, the C region well, but not the D, and vice versa here for A, but not B. So that is similar to our classic ideas behind linear alignment, where we're just changing it so that we have two paths here at the region B and C encoded in our pangenome reference. And that can mean we can represent it more effectively, the true diversity inside this population. If we resolve this more precisely, what we're thinking about is the k-mers, where we have a particular length here, and we might have two alleles, and we can represent that at k-mer level. We can also think is that we're mapping our reads across here, across this region, and read might map here to C or to A, but it might continue on there. And we can contain that in our graphical representation. What is advantageous about this is that we can find that we get better mapping at more complex regions. So our reads can map across here to different variants that are present. So we have one here mapping to allele A here and to CAC and then to the end here and so on. And that's one advantage that's known for graphical representations of multiple samples within a single reference as a pangenome reference. For example, if we have a traditional reference genome, we might have an insertion in our sample which is not present in a reference, and that would mean that we might have a SNP found here nearby in pink. I might have a sample here which contains an insertion, and that may contain a region that's similar with a SNP to this region here. And then if we lack a graphical reference, this bundle of reads will be effectively lost. And when we map our reads to this region, we might get mistaken inferences at this similar site because it depends on whether this and this both have the mutant allele inside our sample. So we find that generally that the pangenomic reference will resolve true mutations more effectively. So we can think of this in this way here, where we have multiple samples here, red, orange, yellow, green, blue, indigo, violet, and we have different reads associated with them. We can construct a variation graph from these. So some might have alleles A and G here, some may have a conserved region CCTA, Some may have or not have this deletion of CGGA, and some may have, all will have this conserved region, but some may have an insertion as well of CCC. Yeah, in truth, the insertions and deletions, depends on your perspective, they're affect both indels. And what we can then do is extract from this variation graph representations known as genome graphs for each of these samples. So if we have our red sample here, its path may go from a conserved region in black here at the start to the allele G, and then to CTCA, it may lack this deletion, and then we will go into that conserved region TGTA through CCC here with insertion to AGAT at the end. And for the orange sample, we might have a similar path all the way through, maybe, but maybe it lacks that insertion. The blue one, we have that G at the start, but then it may also lack that deletion, and it may possess the conserved region and then also lack the insertion, like the orange path. And then we have the pink mauve path here, which again contains the conserved region, lacks the deletion, and also lacks the insertion at the end. And we got the other variants. We have one in the green one, which contains this deletion, has the conserved region, contains the CCC region, and so on. So each of these contains a genomic path that's reflected in this reference. And obviously, computationally, that can be more efficient. So one also question that's related to this wider area is the classic one of more samples or more coverage. And typically, if we're looking at epidemiological situations or sample situations where there's a lot of population level diversity, wild population, typically their sequencing more samples is better, even if they're low coverage. So there's more information to be gathered from that. And that's because the total SNP diversity is reflected in the diversity of the different samples. So that will dramatically improve our population level references, inferences, and same for our epidemiological inferences. They'll be much more stronger if we have a kind of broader sampling. If we're looking at in vitro systems where it's not a unbiased sample, it might be different, where higher depth can tell us more about the evidence supporting particular mutations. So that might be different. We also have other things that are being developed, like genomic VCFs. So that represents samples more effectively, including more information about the blocks, matching the reference and their quality scores. And contains information about all the sites that are present, not just the SNPs and indels inside a VCF. And there's more on that call format down here at this link. So there's more tags that are in there. So it's kind of different to a VCF file. So that you can see that we have a non-ref symbolic link listed in the alternate allele field if there's evidence of a mutation present. So you can see that here for T, we got non-ref listed there. Whereas for the other sites adjacent to it, we don't have evidence of a change. And then there's kind of additional information you can add to the information field containing information, the block ends and so on, the haplotype block ends. And then there's a nice review here at this link, which outlines, for example, different mutation calling options. So we have our traditional one where you have particular reads and they're mapped to a linear reference that I've been discussing here. And that's based on read mapping. And that lets us detect SNPs and it lets us detect SNPs well. We can improve that by mapping to a pangenome reflecting the diversity of variants that are present in a wider population, and that will improve our resolution. We also should bear in mind that there's also approaches that are based simply on the assembled genomes, which can be effective if we've already done the mapping part previously. So that can be compiling different resolved sequences, or indeed it can be in situations where the different samples that are being assessed are very, very genetically divergent. where might be conserved regions of the references are being examined. So that's a slightly different approach. It's assembly-based rather than mapping-based, and that can be effective as well, but it's more effective if we have distantly related samples, whereas if we have very, very similar samples, so say more than 98% identity, mapping-based approaches should work well. So that kind of briefly outlines future developments in this area, and please see the demonstration videos for more hands-on guidance on how to implement these things in practice.